Hi, welcome to this last scheduled lecture for uh, s- Introduction to Statistical Mechanics in Soft and Active Matter Systems. So we were discussing few problems and we were solving those problems. So now let's uh, continue further discussion about the different problems. Okay, so let's see different kind of noise in electrical circuit. Okay, so let's assume that this will be problem 4. So problem 4 is consider the electrical circuit drawn below. Okay, and the circuit is made of resistor of resistance R and a capacitance C. Let's say the charge Q stored in the capacitor is 0 on average. Okay, but can be fluctuating. That means positive. When it is fluctuating around 0, that means positive or negative. So it's positive or negative due to the thermal fluctuations thermal fluctuations of charge carriers. charge carriers Answer the following questions. Okay, so question 1 is the fluctuation of Qt is described by the following equation, let's say. Okay, r q dot plus q by c minus r of t is equal to 0. Let's say this is an equation 1, where psi r t is the fluctuating voltage. The fluctuating voltage. Now this, compare this equation with Brownian motion. Comparing the equation with Langevin equation. Langevin equation show that the fluctuating voltage satisfies the following equation, which is T 0 is equal to 2r kBt of delta t, and also calculate the time correlation functions q of t, q of 0 and its average, and I of t, I of 0, which is current, where current is defined as IT as q dot t, means differentiation with respect to c, is the current flowing in the resistor. Okay, and this is R. So this is R, this is the capacitor this is C, let's say this is charge Q and voltage is psi. So let's this is the figure. Let's do the solution of this problem. So now this electrical circuit is analogous to the Langevin equation. So let's say if the system is macroscopic, if the system is macroscopic, the charge Q in the capacitor obeys the equation in the macroscopic system. This psi RT will be 0, that will become RQ dot plus Q by C is equal to 0. So that makes it Q is equal to some constant, let's say Q naught e to the power minus T by RC. So at equilibrium T tends to infinity, or T tends to, at equilibrium Q is 0. Now in very small systems Q fluctuates, right? Now in small systems, now in small systems Q has some fluctuating values. So Q fluctuates in time, and the distribution of Q at equilibrium obeys the Boltzmann distribution. The Boltzmann distribution, because at equilibrium every system must satisfy that equations, and that what is that Boltzmann distribution? That is P of Q is equal to or proportional to e to the power or exponential of minus Q square by 2C kBT. Why? Because Q square by 2C is the potential energy, right? And mod of Q square should be capacitance time kBt. Now to see these random fluctuations, and potential term is a random voltage is introduced. Now to account this fluctuation, to account this fluctuation, a random voltage which is psi r of t is introduced in the equation. And the voltage psi r of time is a result of the random motion of charge carriers in the system. So if that is the case, and taking clue from the Langevin equation from the random force, we can write so, and its time correlation function is assumed to have the following term. What is the term? Is psi r t and psi r t prime is equal to a of delta t minus t prime. Now that a should be calculated from this distribution of q square. Okay, so and this a is calculated using the formula for q square. Q square of t, calculating the Langevin equation. So if you repeat the same equations, we need to do the similar thing. Just do this thing. Now from similarity of the equation of Langevin, we can say that q corresponds to the position correspond to the position of the oscillator system. R corresponds to friction coefficient, friction coefficient, coefficient and C is the inverse of spring constant. So similar to the Langevin equation for Brownian motion in a harmonic potential, right? So using that same relation, you can promptly rise. So for since for Brownian particle in harmonic potential has the following following relation following relation that we have calculated, that xt of x0 was kbt by spring constant k e to the power minus mod t by t. So by analogy we can write q of t times q of 0. So kbt. Now spring constant is inverse of the spring constant, so this will be c. So you can write like c for 1 by k kbt, and it becomes c to the power minus mod of t by tau. Okay, now we just calculated few this x dot t, x dot 0 is 2 dt del t, and this thing. So and we have also calculated that x dot t, x dot 0 as kbt by k e to the power kbt by k e to the power delta t kbt by k kbt by k to kbt by k of delta t minus d by tau minus d by tau means kbt by gamma. So kbt by tau square, kbt by k into tau square, kbt by tau square So here then tau was gamma by k, so here it will be gamma by k, so friction coefficient gamma, so rc, right, rc. Similarly kVt by k into 1 by tau square to the power minus mod t by tau. So now use this relation, you can write this is kVt by gamma, sorry, this will be kVt by gamma, kVt by gamma. So kVt by gamma means 2 kVt by r delta t minus kVt by k is c, so c kVt times tau square means rc, so 1 by rc whole square into to the power minus mod of t by tau, which becomes, if you take 2 common, then 2 kVt by r into delta t, c cancels out 1 by c, so 1 by rc is 1 by tau, so minus 1 by 2 tau e to the power minus mod of t by tau. So basically that will be the expression, so that will be so that will be the expressions from the similarity thing, right? So what we have done here, we written this equation and we got to know that at equilibrium it will be 0, and in small system, let's say if it is not macroscopic, so that q will be fluctuate around the equilibrium with this thing, and we then found out that there is some similarity for the Langevin equation for a Brownian motion in a potential, let's say harmonic potentials, and there the one-to-one correspondence for the charge with the position of the oscillator system, and r correspond to the friction coefficient gamma, and c is the inverse of the spin constant k. So using this, the tau, the characteristic time or relaxation time scale will be gamma by k, which will be rc. And so now we will use the relations which we have earlier calculated for time autocorrelation for position, and which happens to be kVt by kappa or kVt by k to the power minus mod t by tau. Okay, and so by analogy, since this position becomes the charge, so then k spring constant is 1 by c, so we substitute that and we have got the autocorrelation of the charge. Similarly, we got to know that this speed autocorrelation, the autocorrelation of velocity is like this: 2 into kVt by gamma delta t minus kVt by k into 1 by tau square to the power minus t modulus of t by tau. So similarity you can write I dot t, or time autocorrelation of current will become, we just substituted in that expression for gamma r, for gamma we have written r, and for k or spring constant we have written 1 by or inverse of capacitor, and we have got this formula, this expression. Okay, so that's quite obvious. Okay, so let's do one more problem. So basically these problems are mainly conceptual one. So problem 5 says, consider the equation of motion, equation of motion, motion of particle with inertia of a Brownian particle, Brownian particle with inertia BP is, let's say, let's write it BP, Brownian particle with inertia term included, like m d2x dt2 is equal to minus gamma dx dt plus fr of t plus f external of t. Okay. So this is random force, this is external force, where fr of t is random force, random force, and f of et is external force. Okay, now answer these following questions. Calculate mean square displacement of the particle, of the particle, sorry, first calculate the mean displacement, mean displacement, displacement of the particle, of the particle x of t minus x of 0 equilibrium, or so it's not equilibrium since it is external drive is there, f of e when the external, when the external force is applied, is applied in a stepwise fashion, in a stepwise fashion at time t is equal to 0, that is f of external t is equal to f of external then theta of t. Now using the generalized using the generalized Einstein relation using the generalized Einstein relation, calculate the mean square displacement of the particle at equilibrium, which is x of t minus x of 0 its squared equilibrium 0, and C calculate the velocity correlation function x dot t x dot 0 equilibrium 0 at equilibrium okay. So let's do this. Now if you take average of this equation, then this term will be 0. So let's take this equation as 1. So solution, if we take the average of equation 1, then this random force term, this becomes 0. So equation 1 becomes m d2 mod x dt2 is equal to minus gamma d of mod x dt plus force of external. Okay, so that actually becomes this. So at time t, t is equal to 0, the mean x and d mean of dx dt, this velocity, are 0. Now solving this equation will give you this. Remember, this kind of equation we have solved in this when we have talked about the coupling equation. So this will become xt will become f of Osmolov-Quist equation gamma t minus tv into 1 minus e to the power minus t by tau. Okay, now correlation function. So the response function is obtained. So the response function for this equation of motion should promptly become chi of t is equal to 1 by gamma into t minus tau v, similar like this, tau v 1 minus, only the prefactor changes, e to the power minus t by tau v. Okay, hence from generalized hence using generalized Einstein relation generalized Einstein relation will give xt minus x0. Please refer to the lecture. At equilibrium at time is equal to 0, that should become 2 kbt into the response function, that becomes 2 kbt by gamma into t minus mod t minus t minus tau v into 1 minus e to the power minus t by tau. Okay, and this agrees with the for the normal Brownian particle. Okay, so this we did, huh? Okay, so now from this equation, let's say this is 2, from equation 2 is correct for t greater than 0 and for general t x of t is x of 0 whole squared equilibrium 0 becomes 2 kbt by gamma into mod of t minus tau v into 1 minus e to the power minus mod of t by tau v. Okay, so the velocity, the velocity correlation function is given by x dot t into x dot 0 0 is equal to half d2 dt2 x of t minus x of 0 whole square equilibrium 0. Now we will use the formula that we have previously did. So basically that promptly follows. Now using the formula bdt of mod t should becomes theta of t minus theta of minus t. Okay. Similarly, if you write ddt dt2 of t, then it becomes, for here this will be delta t, for here this will be again delta t, so that becomes 2 of delta t, and dt2 e to the power minus alpha t is equal to minus 2 alpha delta t plus alpha square e to the power minus alpha mod t. So now you can use these relations explicitly in the expressions. So substitute those values and see what happens. You have to just do the algebra here. You have to play around the terms here. The amount of calculations we have done, this should be simple. this is nothing compared to the amount of uh, problem we have solved. Okay, so now if you substitute this thing into this equation, then we have x dot t x dot 0 equilibrium 0 means t is equal to 0, that becomes 2 kbt by gamma tv e to the power minus mod of t by tau v is equal to 2 kbt by m 2 kbt by m times e to the power minus mod t by tau v. How it is happening? We are just basically substituting this value. So for mod t, this will be 2bt by gamma. So mod t will become this. Mod t will give you 2 delta t. That's why 2 delta t. And that's 2 delta t. And here from this expression, that 2 delta t, that will cancels out, and only thing will remain alpha square. So here alpha means 1 by tau v. That's why 1 by tau v square is there. And 2 kbt is tau v cancels out, and it becomes 1 by tau v. So that's why 2 kbt by gamma tau v. Okay. Okay. So it is quite simple. Okay. So let's do one more problem, and that will be the end. Problem 6. These are very big problems. Let's consider two Brownian particles connected by a spring. Let's say two Brownian particles and they are connected by spring. It's a harmonic spring. Okay. And the Langevin equation for those system, for those two particles, the Langevin equations for their positions x1 and x2 are written as this is gamma dx1 dt is equal to minus k x1 minus x2 plus f r1 t. Similarly, gamma dx2 dt is equal to minus k x2 minus x1 plus f r2 t. If there's a thing, then give the answer to the following questions. Suppose that a constant force F1e is applied to the particle to the particle 1 for t greater than 0. Calculate the average displacements calculates the average displacements of the particles x1 t x1 0 at f1 external and x2 of t minus x2 0, which is f1 e in this situation. B. Calculate the time correlation function x1 t minus x1 of 0 whole square and its average, and x1 t minus x1 0 times x2 t minus x2 0 times and their average using fluctuation dissipation theorem. C is discuss the behavior of x1 t minus x1 0 whole square and its average at short time at short time, that is t is very less than gamma k, and at long time that is t very greater than gamma k. Okay, basically the particle is like this. So this is x2, this is x1, and this is drawn by this constant force F1e. Okay. Okay, so basically we'll write the equation of motion. So let solution let xit be the average of xit, like the when a force F1 external is applied is applied to the particle particle 1, that is xit is average of xit this, where I is equal to 1 and 2. So xit satisfy the following equations. So xit follows or satisfy the following equations. What are those equations? Gamma dx1 dt is equal to minus k x1 minus x2 plus f1e, and gamma dx2 dt is equal to minus k x2 minus x1. Let's say this is equation number 1 and this is equation number 2. Now this is a coupled equation, and the solution of this equation under the initial condition x1 of 0 is equal to x2 of 0 is equal to 0 is given by x1 of t is equal to chi 11 t of f1 e. Similarly, x2 t is equal to chi 21 t is equal to f1 e, with chi 11 t is equal to t by 2 gamma plus 1 by 4 k, t by 2 1 by 4 k into 1 minus e to the power minus t by tau. Similarly, chi 21 t becomes t by 2 gamma minus 1 by 4k into 1 minus e to the power minus t by tau, where tau is equal to gamma by 2k. Hence, we can write after a little bit of algebra, x1 t minus x1 of 0 whole squared is equal to 2 kbt. So this is like similar response function things that we have done in the class for external potential and the generalized Langevin equation, and this becomes 2 kbt into t by 2 gamma plus 1 by 4 k into 1 minus e to the power minus t by tau. Similarly, this fluctuation x1 t, x1 0, x2 t, x2 0, the correlation of this fluctuation, if you calculate this, then this becomes kVt into t by 2 gamma minus 1 by 4k into 1 minus e to the power minus t by tau. Now for she let's use for the how it behaves under the regime. Now see, for t very less than tau, your x1 t minus x1 0, its squared and its mod becomes 2 kbt into t by 2 gamma plus t by 4 kappa tau. Okay, now tau means gamma by k, so k cancels out. This is 4 gamma, so t by 2 gamma, t by 4 gamma, that means it becomes then, sorry, tau is gamma by 2k, so this will be 2 t2 by gamma, t2 by gamma, so 2 cancels out and it becomes 2 kBt by gamma into T. So this is same as for isolated particles that we did earlier. So this is same as that for an isolated particle in a short time. The particle moves independently of other particle. Okay. On the other hand, for t very greater than tau, x1 t minus x1 0 whole square, it becomes kBt by gamma into t. That means the particle motion is slowed down. Okay, that means the particle motion is slowed down for long time. This is because the long time behavior of connected particles is determined by the motion of center of mass, right? For a two particle system, center of mass, and the diffusion constant of the center of mass of the present system is given by kBt by 2 gamma, and this equation, let's say 3, and equation 3 is the same as the mean square displacement mean square displacement of the center of mass of the center. Okay, so that concludes our discussion, and that concludes this course. So I would like to congratulate all of you that you have been through this course, and you studied along with this. I hope that whatever little I could help you guys in giving some materials, or clearing your doubts, or like giving some insights, or clearing the concepts. If it is helpful for you guys, I will be honored, and I'll be very much happy. So hopefully we will meet again for for a different course, and I thank you guys for taking this course. Okay, so all the best for your future endeavors, and I'll stop here. Bye.